Okay, so in the last video, we learnt about the Bellman equation, which characterizes the value function of the optimal policy. Now, the Bellman equation might still look very difficult. So maybe we've made progress, but if we can't solve the Bellman equation, then we still haven't really made any progress. But it turns out that there are multiple methods of actually solving the Bellman equation, which are practical. So in this video, I'm going to show you a method called value iteration, which is a numerical method for approximating solutions of the Bellman equation, so approximating the optimal value function. And we can see this as basically a learning method. And value iteration is sort of 50% of reinforcement learning. So by the end of this video, we're really going to be kind of 50% of the way to the basic idea of reinforcement learning. First of all, let's see why we actually care about the value function. So if it's so difficult to solve the Bellman equation, why should we care? Well, if we know the optimal value function, then we can get the optimal policy from it very easily, because the value function allows us to turn a infinite optimization problem, that is, find a policy that will optimize this kind of infinite sum, into a finite problem, namely this one. So the optimal policy in any given state should choose the action which maximizes this value. And as long as V is known, we can just work this out. Right? This is just a value that we can calculate, and then we can just loop over all actions to compute this argmax. So yeah, so knowing the value function allows us to reduce finding the optimal policy to a very simple optimization problem. It's just a finite one that we can just kind of brute force. Okay, so the idea of value iteration is that we turn the Bellman equation into an iteration procedure. So the Bellman equation has two copies of the value function, one on the left and one on the right. And what we say is that the one on the left is going to be kind of the next estimate. So we turn it into just an iteration. So we're going to start with any initial estimate. So a common one is just to say that the initial estimate of the value of any state is 0. At this point, so previously I have subscripted V by the policy, but now I'm going to change course and start subscripting V by just by the iteration number that we're on. So the initial one is going to be V sub 0. So that is to say our initial estimate, V sub 0, is going to say that the value of every state is 0. Now, if we have any old policy sigma, we're going to say that the next estimate, so if we know Vi, then the next one, which is Vi plus 1, is going to believe that the value of a state Q0 is going to be this expectation. It's going to be the expected value, the expected current payoff plus once discounted value according to the previous estimate Vi of the next state Q1, where U0 and Q1 are chosen according to conditionally given the initial state Q0 and the action A given by the policy sigma. That's for where sigma is any policy. If sigma is specifically the optimal policy, then we can say that Vi plus 1, the next estimate, given the initial state Q0, is going to be the maximum over all actions that we could have chosen, or that we could choose, of the expectation of this thing, given, so where U0 and Q1 are given by Q0 and A. So remember that, again, the conditional probability of joint probability of U0 and Q1 given Q0 and A is exactly the defining data of the MDP. Now, here's the magical thing, is that this procedure always converges to the optimal value function, no matter what our starting estimate is. This is a kind of very kind of magical theorem that says that this always works. Not only does it always converge, but it's often fast enough to be practical as well. If you care about the mathematical foundations, this happens because of the contraction mapping theorem. So the VIs are points in a function space, and we can put a metric on the function space and show that this iteration is a contraction mapping, and that guarantees convergence for any initial estimate. Okay, so that's the mathematical version, but we can also go towards implementation of this by noticing that Q is just a finite set of states, and so we can represent the value function, which is we can represent any value function, which is a function from states to real numbers, is just a vector. It's a vector of real numbers whose length is the number of states. So if we have 5 states, then this is a vector of length 5. Value iteration, like this procedure, we can implement this very efficiently. All we have to do is we have to loop over all states and all actions, and then we can just modify this vector in place. So the only kind of potentially nasty looking thing in this formula is the expectation, but we can just expand that out by we're just looping over all states that we could reach from following the action in question. So we need to loop over A's in order to implement this max, and then we need to loop over Q1s in order to implement this sum. And then we have kind of the weighted sum of these terms. That's the payoff that we could get from transitioning from Q0 to Q1, plus the discounted value according to the previous estimate of Q1, weighted according to, again, and then this kind of matrix of conditional probabilities. This is fixed. This is our defining data of our MDP again. So from here you can see, like, you can implement this to be very fast. This is just a loop over a few things. Let's look at our old friend, this robot control example, this thing. So suppose we start with the initial estimate that the value of both states is 0. Now, let's just start iterating. So the next estimate for the value of the high state is going to be, well, it's going to be the maximum of 2 things, namely the thing that would happen if we follow the work action, and then the thing that will happen if we follow the recharge action. So for the recharge action, this is easy. We're going to get 0 for the current payoff, plus we're going to transition into the high state with probability 1. So we're going to say what's the value of the high state according to the previous estimate. Previous estimate is that all states have value 0, so 0 plus 0. This is what we'll get for following the recharge action. For following the work action, then we're going to say with probability 1/2, we transition into the same state, and probability 1/2, we transition into the low battery state. It happens, and so in each case we get a payoff of 1, and then we have a discounted copy of the payoff of the state we're transitioning to. In both cases, that's 0. So it happens that this is 1. 1 is greater than 0, so the next estimate of the value of the high state is 1. Similarly, for the low state, if we take the recharge action, we get 0 plus the value of the high state, which is 0. And then if we work, we get this thing that with probability 1/2, we need to be rescued. We get -10 plus the value of the high state. And then with probability 1/2, we stay the same. So we get 1 plus value of the low state. So this term ends up being negative. So 0 is higher. So we say that the value of the next estimate of the value of the low state is 0. And then we can keep going. So I won't talk through these, but it turns out that the next estimate of the value of the high state is going to be 3/2. And the next estimate of the value of the low state is going to be 1. And I just realized this is not quite right because I have forgotten to put in my factors of beta here. There are some missing factors of beta, which means that the answers I got here are not quite right. But in the general idea is right, is that these are going to increase a bit, but in each case, the value of the high state is going to be lower than the value of the low state. And also at each stage, we can kind of report the action that was chosen in order to, so each one of the two choices that we're taking the maximum of corresponds to one of the two actions we could take. The first one is the work action, the second one is the recharge action. So here we see that in the high state, we're always taking the work action. In the low state, we're always taking the recharge action. Okay, there's one other thing, which is, so currently I said we're going to loop over all states. So that's here, we have the sum over all states. We do this weighted sum to calculate the expectation, but we don't actually have to do that. We can optimize this using Monte Carlo methods. So instead of looping over all possible reachable states, all we do is just choose one, but the way that we choose it has to be weighted according to the probability in the Markov chain. So the probabilities which started life in the model, we're now actually in our numerical algorithm going to use those probabilities to make choices in the algorithm. So the iteration is going to be that our next estimate of the state Q0 is going to be the maximum over all actions. So what we're going to do is we're going to loop over all actions, and then for each action, we're going to choose some reachable state, and we're going to choose it in a way that is weighted according to this conditional distribution, the conditional probability of transitioning to that state given the current state and the action. So we're going to kind of choose a Q1 for every A, and then so the choice of Q1 also determines the payoff that we get for that transition, namely U0, and then we're going to modify the value function according to this. So I also forgot to write the subscript here. So this is VI, that's the previous estimate of the value of Q1. And this method also converges technically with probability 1. This also always converges to the optimal value function. So this is an alternative. Often it's faster. This is a kind of optimization of value iteration.